Alright, so here's the derivation for the electromagnetic waves. It's a three-dimensional wave, so let's set up our dimensions. Wave is going to travel along the x direction, and so you have the y and z axes. Here's the electric field component of the electromagnetic wave, and 90 degrees to it you will have the magnetic field component. It wraps around the electric field, so the magnetic field component is B, and the electromagnetic wave will be traveling at the light speed. All electromagnetic waves travel at the light speed. Here's the electric field component as a traveling wave. Here's the magnetic field component as a sine wave. Once again, it's traveling from left to right. We got terminology that we have to define. K is known as the wave number, and omega is known as the angular frequency, which is expressed in terms of the regular frequency. K is something that we need to define further. You will have a hard time finding a proper definition of it. K simply means the number of full wavelengths that you can put in or squeeze in to 2 pi radians. Okay, so number of wavelengths. In this case, we end up fitting in one single wavelength, so K is going to be 1. Or you can fit in 2 full wavelengths. In that, if that's the case, K is going to be 2. Or maybe you can squeeze in 4 full wavelengths. In this case, K is going to be 4. So wave number represents the number of full wavelengths that you can fit into 2 pi radians. That's what it means. Kx minus omega t is known as argument, and the argument simply tells you something about the speed of the wave that needs to be constant. So Kx minus, which means that this wave is not going to speed up if you take the time derivative of it. Okay, so it's going to give you 0, so there's no acceleration. So when you actually take the derivative of that, it's going to be 0. The expression that you're looking at, dx dt, tells you how fast the wave moves through space, so that's going to be your speed. And speed is going to be expressed in terms of angular frequency and the wave number. And you will notice that in this expression, 2 pi's will cancel. So it's going to give us the familiar expression for a wave speed. And the wave speed is a combination of the frequency as well as the wave's wavelength, which we knew that before from the previous lecture. So that's our wave speed. So we came up with an expression for the wave speed. Now let's come up with an expression for the speed of the electromagnetic wave. So we're looking at the electric field component. Notice that the electric field amplitude is increasing by dE. So what's causing the change of the electric field amplitude is the fact that within that region, the strength of the magnetic field is varying in time within that region. So any time variation of the strength of the magnetic field, according to the Faraday's law, within that region is going to cause a circulating electric field, and ds is the area which is going to be integrated in the counterclockwise direction. And then this only component that we're interested in of the electric field along the direction of h. So the h is going to be height of that region, and a represents the area of that region. So the area of that region is going to be h times dx. I'm just going through the mathematics fairly easy, so the highlighted expressions will add up to 0 or they will cancel out. And then at the end, we're going to come up with a simple expression stating that electric field strength is going to change along the x direction as the magnetic field strength is varying within time. So we carry out the mathematics, so the electric field strength is going to change along the x direction. And what's causing the change is the change within the strength of the magnetic field. So we come up with the expression, so both expressions that we came up with will be equal to each other, and once again the like terms will cancel. As a result, we come up with an expression that tells us that the wave Well, it's kind of obvious from the equation that the wave speed is going to be related to the ratio of the maximum value of the electric field to the maximum value of the magnetic field. And that's it. So we have to look for an expression that's going to be the ratio of the maximum value of the electric field to the maximum value of the magnetic field. So that's what the wave speed is. Okay, so we will play the same game again, this time dealing with the magnetic field itself. Notice that the strength of the magnetic field is increasing. dB represents the increase, and what's causing the increase or change is the time variation of the electric field within that region, which causes a circulating magnetic field. ds represents the direction of circulation. So we know from the Maxwell's equation that any time variation of the electric field is going to cause a circulating magnetic field. So, which means that we're looking at the change in the magnetic field in the direction of the integration of the region. Notice that the like terms will either add up to 0 or they will cancel. And at the end, we're going to come up with an expression that looks like that. Alright, so magnetic field strength is going to change along the x direction because of the variation of the electric field strength within that region, time variation of it. So, which means that both sides will be equal to each other, both expressions will be equal to each other, and then the like expressions will cancel out. Alright, and then we will collect certain terms on the left hand side. The terms on the left hand side are related to speed, so it's going to give you speed squared, square of the speed, and then when you get rid of the square of the speed by taking the square root, light travels at the light speed, which means that the light is an electromagnetic field. All right, so that becomes the conclusion of the research paper article that he publishes in 1865. All of a sudden, he runs into a problem. The problem is when he solves the problem, he notices that all electromagnetic waves are traveling at the light speed with respect to a reference point P. Of course, reference point P on paper is a stationary point, but there's no such thing as a stationary point in real life. When you're driving at 60 miles per hour, obviously, you're driving with relative to Earth. Earth is also spinning on its axis, roughly about 1,000 miles per hour. So Earth is not stationary. It's spinning on its axis. And also, it's moving in space relative to the sun, roughly about 60 to 70,000 miles per hour. Sun is not stationary either. It's moving with relative to the center of the galaxy, and our galaxy that we're in is not stationary either, so it's moving relative to other galaxies as well. So everything in the universe is in motion. So when we talk about light speed, question becomes relative to what? Another question that we had that we didn't know how to answer, so light speed is going to be 300 million meters per second or 670 million miles per hour. Question is relative to what? The only answer that you could come up with mathematically is relative to that position P. All right, so this is position P that we're looking at. Relative to that position, it's going to be moving at the light speed, but that position on paper specified as P is a stationary point that you're looking at on paper, and there's nothing stationary. All right. So that was the reason Einstein asked, what if that point is also moving at the light speed? Would that mean that the light is still going to travel at the light speed relative to that point? So that becomes the foundation of special relativity. Another problem with light being a wave comes from the very definition of what a wave is. Wave is a disturbance. It requires a medium that it can disturb. How fast this disturbance is going to travel depends on the tension within that medium, as well as the density of that medium. Light travels at the light speed, which is 300 million meters per second, in a vacuum. There is no tension in a vacuum. There's nothing that makes up a vacuum. There's no molecular density, there's no molecular tension of vacuum. So if that's the case, what is the medium that the light is disturbing in order to travel at the light speed? Because physicists love the idea of having a medium for a wave to travel in or disturb it, they came up with this hypothetical medium, a stationary medium within which the light can travel at the light speed. This medium was supposed to be infinitely rigid with absolutely no density, no viscosity. They called this medium the medium that the light disturbs, a medium that allows light to travel at the light speed, ether. All right, which was first proposed by Christian Huygens, and Maxwell adapted the idea. And in 1787, two physicists in Cleveland, Ohio, in trying to detect ether, discovered that the ether did not exist, which means that there's no medium that the light actually disturbs in order to travel at the light speed. So if light is a wave, given the fact that there's no medium that is able to disturb, how does it travel at the light speed? This was not an easy question to answer. It literally took years. It took 10, 20, 30 years before physicists settled on the idea that the light is a self-propagating medium. It's a self-propagating concept. Any variation of the strength of the electric field is going to create the magnetic field. Any variation of the strength of the magnetic field is going to create the electric field component. So light does not need a medium to disturb. It becomes a self-propagating, I was going to say medium, I don't know if that's the right term. So light is something that self-propagates. It doesn't need a medium to disturb. And that's the concept that physicists settled on eventually. All right, so if light is a wave, if a wave is a traveling disturbance, then how fast the wave travels is determined by the tension within the medium and the density of the medium. In the case of light, there is no such medium to disturb. Light simply self-propagates.